Okay, so yeah, looking at the first derivative, domain, there's no restrictions at all. It's all reals. It's a polynomial. And really, again, algebra 2 happened. You know cubics look like that. I didn't cut it off. So Amir is saying, well, it's coming up, the slope, the derivative is positive until -3, and then it turns around. And he said there's a local maximum there. Why? Because unbounded, it goes, the function itself covers all reals. The range is all reals. So, but right here, okay, local max at x equals -3. And the reason is f prime went from positive to negative. Because that's saying the slope, the y value stopped going up and started going down. Right at that change, right when the velocity is 0, or right when that rate of change is 0, is your maximum. And again, because we know from algebra 2 and pre-cal what this function looks like, there's a local min at x equals +3, because not the slope, but f prime went from negative to positive. It stopped going down and started going up. This is what's called a first derivative test. Cool? Yeah.
Why didn't you know, like, to use the table instead of the number line?
What are my endpoints?
Oh, okay.
So when it's a closed interval and I chop it off, or if I did something mean and I made this like square root, which I have no idea how to, like, I would need a calculator for this. But if I force some kind of naturally occurring domain restrictions, yeah.
Why don't you have to find like the y value?
When do I have to find that y value?
Or like why not here? Like why are we only finding where? Or like when it is?
Okay, you're right. It says find the local extremes. Did I find the extremes? I found where they are. So we would plug the 3's in to the derivative or the function. The function, yeah. And I don't know. Yeah, I'm feeling it. What is it? Does it come out to? So like +3, 27 minus 81 plus 3. And -27 plus 81 plus 3. Whatever that is. 54. $57, this one. So yeah, good point. So did it ask for where does it happen or what are the values? Roxanne is pointing out that he didn't actually answer the question, what are the extremes? Okay. So we're getting to, this is a 2-day thing. The homework is day 32, 33. Today is technically day 32. Look at the homework, do the parts that you can that we get through. But I know that we're not going to finish the concept today. So there will be like, hey, I don't quite get it yet. So we're going to check first derivative test and learn the words concavity, which technically you did in pre-cal, and points of inflection. Been hearing like in the news and in just regular language, people have been saying inflection point, like the inflection point of the war, the inflection point of the political party struggle. Does anybody, what does that mean in just English?
Well, it means the point where it shifts dramatically.
Point where it shifts dramatically. Okay. And we're gonna see what that means in a graph. So that whole, don't draw this, it's in your book if you really wanna like have it. So things that we're gonna start to look at is the first derivative positive? And then first derivative went to zero. Oh, if the first derivative is zero, it could be a maximum or a minimum, or in this case, neither. This, right where it's that saddle point, that's called an inflection point. And so the derivative, the first derivative didn't change sign, it stayed positive. So that first derivative test we just did, we said, oh, it was going up and then it was going down, so that's a maximum. This was going up, took a rest, and kept going up. So it wasn't a maximum. First derivative went up, hit zero, then became negative, that will be a maximum. Was negative, hit zero, became positive, that's going to be a minimum. And you would have to do the table Scalia to say, oh, it's absolute or it's just local. And here, the derivative was undefined, but it went from going up to coming down. So that's going to be a max. Negative and still negative, that's an inflection point. So we're going to work on just looking at a function, not the graph, to see these things. All right. So first derivative test, you might want to write stuff. Okay, so if the first derivative, Hadley, what do you think? If the first derivative changes sign from being positive to negative at some x value named c.
Then it'll be like some kind of maximum.
So it goes, and if you guys want to draw it for yourself, like the derivative was positive, then negative, it's exactly what Hadley said, then it's some kind of maximum. Like local might be absolute, but it's some kind of maximum. Miriam, what do you think about the second one? If the first derivative changes sign from being negative to positive at x equals some value,
We're gonna have some kind of minimum.
so slope was negative, and then it was positive. So if it's continuous, then yeah,
But f is what? At 2.
it would have some kind of local minimum. And I should point out, all of these, the function had to be continuous. If it's not continuous, it doesn't hold. Well, Tom, what if the first derivative does not change sign at all?
It's just like not a local window, maximum.
It's not an extreme. It doesn't change sign. No max, no min. You drove up to the stop sign, took a rest and went. Or you were going negative and you stayed negative.
So is that an inflection point?
Trying to think of situations where it's not, yeah.
If it changes sign like from negative to positive, will there always be a min, like if it goes
Okay, what is it?
down and 0?
First derivative?
Yeah.
Okay, all right, interesting question. So Josh just asked, what if the function has a negative slope, then goes flat, and then goes up?
The slope is undefined at those points.
The slope is undefined at the corners, but critical points are where slope is 0 or undefined, so undefined is fine. That entire flat plateau, I would say, are a collection of minimums. Because if the slope is 0, plateaus like that, that's rock bottom. You can't get lower than 0 in your score on a test, though some have tried. Okay, now let's think about this. If f prime, we're at a left endpoint. And this, like, I don't want you to memorize, I want you to think through it. So Camden, we're at the left endpoint, and we're headed towards the right endpoint. It says f prime less than 0. What does that mean?
It means that if it's like less than
Is the slope positive or negative?
negative,
Negative. So I'm coming from the left endpoint, and I'm going to have a negative slope. So how do I draw the line?
going like down.
Going down. So is the left endpoint going to be a maximum or a minimum? A maximum. So don't memorize it, draw it. Be like, all right, I'm starting on the left side and the slope is less than 0. Slope less than 0 means it's negative. So Camden's like, what do you mean? It's doing like it goes down, like duh. But if you're approached with this on a test, then it's like, what? You're gonna panic, like, how do I know that? Well, just draw it. Left endpoint, and if the slope is positive, just draw it and make a positive slope and be like, from the left side, that's gonna be a local minimum. Okay?
Okay, so if that writing is confusing, f prime is less than 0 and f prime is greater.
Okay, so Amir, they're trying to give you both cases in one phrase to not write so much. So they're saying if f prime is negative from that left endpoint, that f prime is negative from that left endpoint. So we are seeing negative from the left endpoint is going to be a maximum. And then parentheses, same thing. If from that left endpoint it was positive, then it's going to, that endpoint is a local minimum. Ethan, what if it's the other endpoint? The right endpoint. And the slope from this side, I'm telling you, pick one, positive or negative. If the slope from the right side of my, left side of my right endpoint is positive, is B going to be a local maximum, local minimum, or we don't know?
Maximum.
Because why? The slope was going positive until the end.
Yeah.
So, and if it's like, that's the end of the fairy tales. Oh, and then Cinderella, it was all good when she got back from the ball, and yay! And the other one, like it's those dystopian movies, you know. It was terrible to begin with, it got worse, and then everybody died. The end. One big question. No.
I don't know if it was on the last slide or something, but it said local extreme max or extreme, like, they kind of use the two, like, in the same sentence. Is that, like, referencing, like, the lowest of the local? Like, I don't know. There's some weird phrasing. Okay.
I don't think so.
And maybe I was wrong with it.
I don't know, if you can
I
look through
thought
it.
I saw something. but-
Okay, well, if you, I can show you the book and let you look. Okay, turn the page. Okay, concavity. We sort of told you this last year in pre-cal, we're like, oh, it's curvy this way or curvy that way, we call it this. So what concavity means, well, we had an accurate, or a thing to tell you last year to remember which was which. Concave down makes it round. And concave up
Like your cup.
makes a cup. So to see if something was increasing or decreasing, I looked at the first derivative to see the slope was positive or the slope was negative. What am I gonna have to look at? Like, this was changing a lot, then it was changing less, and then it was changing less, and then it was changing less, and then
Second derivative, that's positive.
gotta look at the second derivative. So with the, you stop answering. Nick already knows. Would the second derivative be positive or negative to make this kind of thing?
Positive. Negative and concave down. But no,
Hold on, what did you guys say? Alex, what did,
It's concave down, so the second derivative would probably be negative.
okay, so the second derivative would probably be negative. Anyone have like rationale they wanna add to that? Cecilia?
Like, I don't know, I think of it kind of as something slowing down because it's getting like, the slope is getting smaller and smaller. But like, I don't know how to
Okay,
explain.
so, Sasha,
Well, the second derivative is like acceleration, so it's getting closer to zero. So it's negative.
okay. So, Sophie, what were you gonna say?
Like the function, if like the normal thing is y equals x cubed, if you take the first derivative, it's like 3x squared, then the next, can you just like do it that way and then see what that function's gonna look like? Is that
Okay,
how that, like, works?
So it's good to have the touchstones to get back to the functions you know. So here, let's see. The rate of change, your velocity, your velocity, you're changing many feet per second, you're going really fast here. This was 60 miles an hour, whatever. And then right here, 20 miles an hour, your acceleration is negative. So the first derivative is decreasing, which means the second derivative is negative. All right, basically the thing you need to know, it's concave up. When y prime is increasing, which means y double prime is positive, it's concave down. When y prime is decreasing, which means the second derivative is negative. Any questions or comments? Concave up makes a cup. Concave down makes a frown. Jasper, can y prime be positive and y double prime be negative? I have positive velocity but negative acceleration. Okay. So it's moving forward but less fast. Okay. So Clara, what do you think? Looking which U shape do I want if y double prime is negative?
Concave down.
So the frown?
Yeah.
Okay, which side of the frown would be the part where y prime is positive? The left or the right?
The left.
The left? So here we have first derivative positive, second derivative negative. Some of you on a previous quiz, you said, oh, it's slowing down because acceleration is negative. Well, if you throw anything in the air, as soon as it hits the top peak and starts coming down, it's speeding up. Velocity is getting faster as it's careening towards the ground, right? So the acceleration was negative the whole time. That's not the indicator. So just pointing out on this U shape, for each of them, you can have negative slope, negative first derivative, and negative second derivative. There's a mix and match of all the cases, okay? So I think you guys just wrote this. Concave up means second derivative is positive, concave down is second derivative is negative. Yes? You already have that from a second ago? I just added it to the thing. I want to get to the fun part. Okay. We will just say this. Inflection points, you need to know these two. And unfortunately, there's an extra wrinkle. Critical point, where the first derivative is 0 or undefined, period. Inflection point, and they will definitely ask you on the AP exam. Inflection point is where the second derivative is 0 and undefined or undefined, and the sign of the second derivative needs to change. So someone had said about I think Sophie said, something goes from concave down to concave up, like on that cubic, right there is an inflection point. It's also called a saddle point. Changes dramatically, as Amir said. Everything was going up and then it slowed down and then it was like, wow, total upturn, major change in the plot. Might be embellishing a little bit. Don't want to do this example, it's stupid. The inflection point, we do the first derivative, we do the second derivative, we get, hey, it's undefined at 2, and that's the critical point, but it's not. Why is x equal 2 not a critical point or an inflection point? Because the function itself is not defined. Like, I hate this example, I need to delete it. This one's a challenge. Give it a try.
So if you put an exponent in x4, does it multiply?
Sorry?
If you power an exponent with an exponent, does it multiply?
This is not power rule, if that's what you're asking.
No, I meant like if you multiply, like if you raise the negative x to the power of 2, does it become negative 2x? 2e to the power of negative 2x is what I'm saying.
I'm still not.
Like,
Let me see.
okay, so like you saying like 2e to the power of negative x is just going to the power of 2. Could you simplify that to 2e to the power of negative 2x?
No. Nope.
I thought that was possible.
You're getting the rules with natural log mixed up with this. I can't bring the exponent down I think you're thinking of this. That we can do, because it's a rule of logs, but this is not log. I can't do that with exponents.
I think you just stick with X squared rules, like power to a power, and then multiply.
Okay,
But can you not do that there? It's so old.
well,
Why can you not do that there?
Well, this is e to the negative x raised to the x. I'm multiplying these things. It's not two x's, it's x times x.
Oh.
That worked, that did it. Well, let's find inflection points. What do I need to do?
So,
First derivative, oh, find the first derivative and the second derivative.
yes.
Any volunteers to do the first derivative? Yay, it is just such a joy writing on the board. Luke keeps looking down like, no, I'm not doing it. Lily, first derivative, e to the stuff, what's the derivative of e to the stuff? It is exactly itself. So e to the stuff is e to the stuff. Then there's the wrinkle. What else do we need to add to it? Derivative of stuff, which is, Lily, what's the derivative of stuff? Negative 2x. Okay. First derivative, not so bad. Second derivative is a stinker. Gus, second derivative? Is it just e to the stuff again?
Yeah. Well, no, we have to do product rule.
Product rule. There's two pieces. Okay, so product rule. What do we do? Centric on this.
So derivative of something times.
Okay. So,
Sorry, I didn't realize I had to do product rule.
sorry.
We're good.
Massimo, are you done? What'd you get?
I got negative 4e to the negative x squared plus 8x squared times e to the negative x squared.
Okay, so first times the derivative, second, I gotta do it in pieces. So you can move that forward wherever you want to, but I'm calling the first term negative 4x. So negative 4x times the derivative of e to the negative x squared is e to the stuff times derivative of stuff, plus second times the derivative of the first. Yep. Okay. And some Millette told us, take that and set it to 0. Huh. So this is 8x squared e to the negative x squared minus 4 e to the negative x squared. Without a calculator, how in the world are we gonna do this? All right.
I just factored out 4e to the negative x squared and then I set both of them, both things equal to 0.
So taking 4e to the negative x squared out, what do we have in the first term still left?
So you have 2x.
Don't reboot. 2x squared.
Squared, yeah.
So we take each of these terms, set them to 0. Camden, when is 4e to the negative x squared 0?
0.
At 0. 0 squared is 0, e to the 0 is 1. You don't know what you think, when 4e to the negative x squared 0. Okay, e to the negative 10 is 1 over e to the 10. Does it, right? When does this equal 0? It doesn't. That graph is gonna look like this. It's an exponential derivative. Never, ever, ever 0. This one, okay, plus or minus root 1/2. Okay, so inflection points, are they both inflection points or do I need to test something else? Sydney, what do you think? What, the definition, yeah, we need to test something else. What do we need to prove?
Like the sign changes.
The sign of what?
The second.
Okay, so we need a number line, and we are testing not the first derivative, but the second derivative with those values. Because definition of an inflection point, second derivative is 0 or undefined. So Millette told us to find those. There, Millette, online, there you have them. Sydney now says we need to check if the sign changes. So Roxana, what am I plugging in where?
They're plugging it into the factor version of the second derivative.
Plugging it into the factor version of the second derivative?
Yeah.
Good idea. Do I need to plug into this first term, or is this first term always positive?
You don't need to because it doesn't end up happening.
This one, it's always positive, so I don't care, I'm gonna ignore it. So putting in negative 18 million, what do I get, positive or negative?
Positive,
Putting in 0,
negative,
putting in positive 5,000.
a positive.
So Eitan, what's the conclusion? Where are my inflection points?
Plus or minus root 1/2.
And don't give y values, because the y values don't make sense. Most of you have been plugging back your critical points into the first derivative. I'm like, well, yeah, it's gonna be 0. That's how you found them. So don't give those as coordinates. Maybe you need to go all the way back to the actual function, but we're not gonna do that. So it's inflection points at these guys because f double prime was 0 and f double prime changed sign. Graded 800 and something of these last June. They do not give you the point if you just say second derivative was 0. And it's not just 0, it's 0 or undefined. Sydney?
So if the second derivative is e to the something, is it never going to go 0?
Okay, can I clear this? For whatever reason, you guys get panicked when it's an e. So let's just look at 2 to the x. Going this direction, instead of doubling each time, I'm doing a half. If I have an exit card I don't need anymore, I give you half the paper each time. I'm only giving you half though. I'm very generous, I give you half of everything I have. Am I ever gonna have 0 paper?
No.
No. So they're never gonna get 0, no, it's gonna get really tiny and there's gonna be a big old mess on Eitan's desk, but I'm still being really generous. So it never gets to 0. So those exponentials, is that ever gonna be negative? No. The only time it's gonna be negative is if it's negative the whole time.
So that's the same with anything with x.
So some number where the x is in the exponent and exponential, it's either exponential growth or exponential decay. And of course, remember, they can make it shift. So this, if I shifted it down, it will hit the 0, but they're cheating by shifting. Okay. So this is to get you to start thinking about, well, because it says this, what does it do? Josh, what are you looking up? Seeing if the graph does.
Oh, I was just checking the problem.
Just wondering if it's something fun we should look at. I don't know, like, again, I'm hoping that you don't need to write this, but that it makes sense. If y prime is positive, the curve is going up. It might be going up in a straight way, or it might be up in a curvy way, or it might be curvy that way. What is going up if y prime is positive? Yeah.
What is a situation where the second derivative is undefined and also changes signs? Like, when that's the situation.
Can also changes sign. So it's concave up, concave down.
But like, does that naturally occur in a function that's not piecewise?
Naturally occur.
I
Um,
So that's a weird way of phrasing it, but like, what's a function that actually does that ever?
I can do some strange things with square roots. I'll get you one tomorrow.
Okay.
Naturally occurring, it's hard to see, hard to get those, but they happen. But you're right, it's normally a piecewise function. Y prime is negative. All right, so that means it's either going down in a straight way, or it's curvy this way, or maybe it's like tapering that way. Y prime is 0. Might be a max, might be a min, or maybe an inflection. Or an inflection this way. Yeah, Hadley, question? So eventually, like soon, we're gonna ask you guys to like put these pieces together. Well, if the double derivative is positive, it's some kind of concave up. It might be one half of the smile or the other half. It might be strictly this side or that side. Okay. I don't either, but it's here. Okay. F prime equals 0 and F double prime is less than 0. Annie, F double prime is less than 0. Is it a happy face or a frowny face? Frowny face, because double derivative is negative, so concave down makes a frown. F prime is 0. Miriam, what does that mean that we know about? That it's got a horizontal tangent. Horizontal tangent needs to be flat. Right there. So what is that x coordinate at C? What's happening? It's a max. I don't know if it's absolute or local, but it's a max. So yeah, local max. And so this is, we did the first derivative test as the warm-up. Second derivative test is, okay, this one, it's happy, it's concave up, and this, the slope isn't positive, it isn't negative, it's 0. So right there at that C value, it's gonna be a minimum. Cool? Cool.